Hello. If you should hear me and you should see the desktop now. I think everything is ready. Does it seem okay?
Looking good.
Yes,
Okay,
it looks
Yeah,
good.
we can hear you.
great. All right. So I got, looks like almost everybody's here. Okay. All right. So what we're gonna do is today just keep talking more about grammars. Look at some more examples of understanding how to read a grammar. Okay, and maybe also look at some simple examples. Well, mostly our goal is to learn to read a grammar. The textbook has some nice homework exercises where they ask you to write grammars, and we'll look at some of those. And they're real simple examples. So they're asking you to write very simple grammars. The kind of but you actually, as as someone in computer science, you should be able to learn to read complicated grammars, but you almost never have to write them. It's pretty rare that you ever write a grammar, but it's not. It's helpful to write simple grammars as a way just to make sure you understand how grammars work. But programmers do quite often need to read. Yeah, you see here, like we put it, like a lot of what you do in programming is defined by grammars. Like when you really need to know what a URL or SQL looks like, or what JSON looks like, you go to the grammar to find out. So grammars are great tools for being specific about what you can type into a program. So reading grammars is important, and writing grammars is kind of just good practice. Writing simple, very, very simple grammars is good practice for reading medium complicated grammars. Okay, now I put up on the website the examples we did the other day, and want to finish what's in chapter 1 today. So here's the outline of chapter 1. Here's his outline of chapter 1. We've done a lot of what's in there. We want to do a little bit. There's a few more things I want to talk about in chapter 1 before we start talking about what's in chapter 2. Okay, so so let's go over here. Okay, let's look at this idea of phrase structure and lexical structure. We haven't talked about that too much. Okay, so this is kind of I don't remember where, let's see, where does it go in here? And here's where he starts talking about. This is the idea of tokens. Okay, what we want to talk about is what do we mean by a token? Okay, a token, like he points out, a token is, let me give you an example of how tokens like how the idea of a token matters. So I'm going to go to the Java visualizer, and we're going to look at kind of a famous example in Java. Okay, so int x equal 1. Okay, int y equal 2. Okay, int z equal x plus 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 y. What's that mean? This is not an easy problem, but here's 3 lines of Java. Can you read it? So start thinking. Tell me, what do you think that line 5 means?
Increment x by 1 and then add it to y.
Well, okay. So you would say that means increment x by 1 like this, right? Then add that to y. But why does it not mean add x to the increment of y? Could it be that?
Just going off of basic left to right rules.
There is no left to right rule. Yeah, the trouble is there is no left to right rule. Okay, there is no left to right rule. So for example, here's another one. Int w equals x plus 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 y. Okay, here's a left to right rule. X incremented added to y incremented. Okay, turns out that won't compile. This one's not going to compile. This one will compile. And you're right, it actually does mean X incremented, then added to Y. Okay, that's what it actually does mean. Okay, now here's what this has got to do with. That line can be tokenization is breaking things down into the units of a programming language. There's no unit in Java that goes XXX. I'm sorry, plus plus plus. But there are the plus plus unit and the plus unit. So the question is, how should this be broken up, which we say, the technical word is, how should that be tokenized into units, into tokens? We have two tokens, the plus plus token and the plus token. And the question is, how should those three symbols be broken up into tokens? Okay. And there's one way to do it would be plus 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 Y. Another way would be X plus 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 Y. Here's another way it could be broken up into tokens. It could be broken up into X plus the plus of the plus of Y. All three of those are correct. This could be tokenized three ways. Okay. The plus plus pluses could be either lumped together as 2 followed by 1 by itself, 1 followed by 2 by itself, or individual pluses. Okay. This one means add X to Y, and then what? This means add X to Y, and then what do you do after you add X to Y?
Update X.
Pardon me?
Update X.
Update it how?
You increase it by 1.
Yeah, you increment X by 1. Now notice that's done after you add X to Y. So you take the value of X and you add it to Y, and then you increment it. Okay. This one means you do what?
You add it to Y and then you increment Y.
No.
I think you increment Y first.
Yeah, you increment
Oh, yeah,
Y,
yeah.
and then you add it to X. You add the incremented value of Y to X. What does this mean?
Same thing.
Nope. Because there's no plus plus. See, you can't say lump those together because they're not lumped together. They're not a unit. They have a space between them. So you cannot tokenize this by somehow saying lump these together. There is no post or pre-increment operator here. There's 3 pluses, but there's no plus plus. There's no plus plus. So what does this mean?
Is it invalid?
X plus
Let's
Y.
find out. Okay, let's find out. Let's see which one of these compiles. Okay, so ask the visualizer. Okay, that one doesn't compile. Like I mentioned ago, that one, Java does not know how to break that one up. We'll see in a minute why what goes wrong there. So that one doesn't compile. Let's see about these other ones. Oh, they all compiled. There's nothing wrong with them. Okay, we know what the, okay, now this one, it's not so obvious, but what this one means is a plus plus followed by a plus. So this one, line 5 is line 6. Okay, so line 5 is interpreted by Java as line 6. Line 7, we know what that is. That means increment y, then take the new value of y and add it to x. But what does this one mean? Start telling me. Start thinking through it.
Just x plus y.
Okay, that's actually the right answer. It's just x plus y. But you have to then tell me, what are all these pluses in here doing? It is x plus y. What's this guy? I'll give you a hint. He's not addition. He's not addition. What are they then?
How do you call it? Concatenation?
Pardon me?
Concatenation, you call it?
No, oh no, there's no strings here. No, there's a third meaning of plus. Plus has 3 meanings in Java. Plus means addition, plus means concatenation, but there's actually a third meaning of plus that almost everybody forgets about. And it's being used here.
Is it like when you combine like multiple statements in one line? I'm not sure what that's called.
There's no such thing as combining multiple statements in one line. I'm not sure what you mean. There,
Like if you're writing like a string and then you end the quote and you add a plus and then you
that's
add like a variable.
concatenation.
Oh, okay.
That's combining strings. That's called concatenation. Okay, that's combining strings. You know, that concatenation is that's concatenation of strings. Okay, and yeah, that's combining strings. It's not combining lines of code. You know, you can add 2 strings together. Okay, this guy is not concatenation because there's no strings. X is a int, y is an int. Okay, let me give you a hint.
Positive or negative?
See those 2 lines, 3 and 4? They don't mean the same thing. Whoops, what did I do wrong?
You put a y instead of t in int.
Oh, God, sometimes I can't even see the obvious. Okay. Each one of those minus signs means a different thing. Line 3, 4, and 5, they give you the same answer, but they don't mean the same thing. What's that mean? Think of your TI calculator. That and that don't mean the same thing. Why do I say think of your TI calculator?
One's minus and one is negative.
Yes, one is the subtraction operator and one is the negation operator. Why do I say think of your TI calculator?
Because if you just press minus instead of the plus minus, it's different.
Well, what do you mean? What is it about the TI calculator?
If you do -9, it would be subtracting versus
Well,
the 9. and the
why do I?
plus.
No, you're not explaining it very well. Think of it. What is it that the TI calculator does that's odd about the minus sign?
There's 2 separate ones for negation and subtraction.
Yeah, it has 2 keys. They put it on 2 different keys. There's one key on the keyboard that's subtraction key. There's another key on the keyboard that's the negation key. And they're actually slightly different shaped minus signs. Okay, Now Java does what? It uses the same symbol. What makes this one negation and this one? Oh, this one is the negation operator, but then what is this one? This one is subtraction. This one's negation. What is this one then? This is where the tokenization comes in. This is 1 unit. In Java, that's 1 unit. What does it represent?
Just integer.
Which integer?
I think just -9.
Yeah,
The
in 2's
negative is-
complement. So that's the number -9 in 2's complement.
Okay.
What's this represent then? This is why we're doing a programming language class. Programmers should know what they're typing. When you get into like job interviews and you get into really working on really technical stuff, you'd be amazed at how much this stuff matters. It's not trivial. Programmers need to know what every symbol in front of them means. And you will be quizzed on this stuff and you'll be asked, you need to know what every symbol means. This symbol is not the same as that symbol. It's not the same as that symbol. Okay, so we're learning how to parse and tokenize these things. Okay, this one's negation of what?
+9.
Yes, the negation of +9. This one is what?
-9 and 2 complement.
No, yeah, so this is a number followed by an operation. If you looked at the compiled code of this, you'd see 2 steps. You'd see the number 9 is loaded into a register and then it's complemented, negated. That's 2 steps. This is loading a register with 1 number, the number not -9 in 2's complement. So this is actually a billionth of a second faster than this, because it takes about a billionth of a second on a modern computer. They do about 1 operation in a billionth of a second. This loads 9 into a register and then negates it. So that's 2 steps. This loads a register with -9 in 2's complement. What does this one do?
So a subtraction of 2 integers.
Yes, so it would, how many steps would that be?
3.
3. Load what?
Load 0.
Load 0 into 1 register, then load
9.
+9 to another register, and then
Subtract.
subtract the 2 registers. And you would see that, like that's one of the things we, in the architecture class, I used to do these examples in the architecture class, because you could actually compile this and look at the machine instructions and see that they compiled to 3 different things. This one compiles to the negation of +9. This one compiles to loading the 2's complement number, -9. And this loads 0 and 9 and it subtracts 9 from 0. Then it subtracts the 2 registers. This is the negation operation. This is part of the integer literal. Okay. This is tokenized as 1 unit, the integer literal representing -9, which means that it gets loaded as -9 in 2's complement form. This is subtraction. Okay, now go back over here. What's this?
X plus +y.
Okay,
Oh, yeah,
x
that one.
plus is x plus the positive, it's x plus the positive of y. This is the positive operator, which is the complement of the negative operator. The negative operator takes a number and negates it. What does the positive operator do? It takes a number and does what to it? If this takes a number and negates it, what do you think that does?
Absolute value.
No, that's a function call.
Makes it positive.
But
No.
it already is, so it does what?
Leaves it alone.
It multiplies
alone, yeah.
positive.
It just leaves, it actually doesn't do anything. It's technically allowed it, you can write that, and it doesn't do anything. That's just the number, that's just a fancy way of writing the number 9. And then this is just another way of writing the number 9. This actually is an operator, but it doesn't do anything. Okay, so the compiler is smart enough to skip it, but it's technically the positivity operator. It's kind of like it's the complement of the negativity operation, the negation operator. So it's there, okay, but it doesn't do anything. Similarly, that's the literal positive 9, which is the same thing as, just the writing 9, but you can write that. You're allowed to write that. That is the literal negative 9, which is not the same thing as that, which is the negation of 9. These things matter. If you wrote a loop that looped a billion times and your loop was that, you might actually notice that the loop was a little bit slower than that, because that actually does 2 steps where that does only 1 step. It's a minor thing, but as you learn more about programming, you start realizing that these minor things can add up. You really do need to know what everything on your code page means, because little things can start adding up, and they sometimes add up to weird bugs, and they also can add up to weird hacking errors and things like that. Knowing what your programs are really doing in tremendous detail can matter. Okay, so there is this idea of the positive 9, which is just a simple shorthand for that, which is not the same thing as, it's almost but not quite the same thing as, well, this and this are exactly the same thing. Okay, that and that are the same. This is not quite the same thing, but the compiler pretty much just throws that plus sign away, so it pretty much acts just like this. On the other hand, when you put minus signs in there, they really are different. Okay. This is the negation of 9. This is negative 9. This is 0 minus 9. So 3 steps to do that. 1 step to do that. 2 steps to do that. Okay. Over here, this is actually X addition of the positivity of Y. So what happens is the two of the pluses just disappear, and this just ends up being X plus Y. Okay. Now notice that this guy could be 3 pluses in a row, could be tokenized either this way, or this way. Java does it this way because of a rule in Java. The rule in Java is you always build the largest token you can. So out of these 3 pluses in a row, you could build a big token followed by a little token, or you could build a little token followed by a big token, or you could build 3 little tokens. The rule in Java is build the biggest token you can. And that rule has a funny name. It's called maximal munch. Okay, see, maximal munch tokenization. See, so you can go read. Programmers love to give names to things, so we actually have this idea of the maximal munch tokenization rule. Build the biggest. See, you munch off as large a token as possible. Okay, so you always munch off the largest token possible. The largest token you can build, the largest token you can get out of plus 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 is the 2 pluses. So that becomes the post increment operator. Now go back over here and see why this one doesn't compile. Can anybody see now why this one doesn't compile? I can make sense out of it. But Java doesn't know how to make sense out of it. Does anybody see why? What goes wrong? What's going to go wrong here? Use maximum munch. What do you carve off out of 5 pluses in a row? First, you get what?
I think someone put it in the chat, Professor.
Oh, don't write things in the chat because I don't have I can't focus one eyeball on one screen and another eyeball on another screen. Yeah, say things.
Sorry, what I put in the chat was, does it do x plus plus and then space plus plus
Yeah,
space plus y?
Because it keeps doing the maximal munch. So the largest thing it can carve out of this is plus plus. That leaves these 3 by themselves. What's the largest thing it can carve out of 3 pluses? 2 of them. Okay. Now, why doesn't it compile?
Because of that middle plus plus.
Yeah. It's trying to do plus plus of the plus plus, and that's not allowed. You can't increment something. You can only increment a variable. The plus plus has to be on a variable. So for example, you can't do things like, this doesn't make sense. You can't write plus plus on an expression. You can't write, oh, here's another thing that doesn't make sense. That's not 6. That won't even compile. You can't say 5 plus plus and think that means 6. That won't compile. Plus plus can only be written directly on a variable because it means take what's in that variable and increment it after you've used the variable. So you can't do the plus plus of a plus plus. And you can't apply it on this side either. You can't pre-increment something that's, see, it can't treat this as a pre-increment of plus y because of that. Well, it could if it treated it as, here's the problem. If it treated it as a pre-increment of y, then there's nothing to do with the post-increment of x and the pre-increment of y. There's nothing done with them. See, there's no operator in between them. So it can't treat this as the pre-increment of y either. So it just says that this doesn't compile. So 5 pluses in a row don't compile. The 5 pluses don't compile. Even though I can make sense of it, the Java language isn't smart enough. The tokenizer is not smart enough to tokenize it that way. The tokenizer uses the maximal munch principle, and the tokenizer tokenizes it this way, and then it won't compile. And if you want, then you could tokenize it yourself. You can tokenize it yourself, and you do that, and now it compiles. Okay, so watch. One, two, 3, 4, 5 pluses will not compile, but this one will. Okay. So that one won't compile. But if I tokenize it myself, it compiles. And there are actually several places in languages like C and C++ where you can't count on the tokenizer to do the right thing. You have to tokenize things yourself. There are several weird little places in the Java and C++ language where like here, the tokenizer came up with its own idea of what that meant. Okay, the tokenizer turned it into that. But that may not be what you meant.
Yeah, in line 9, what if the last 2 pluses were minus?
Oh, good question.
Because then that would break up the maximum munch thing, right?
Yeah, let's see. Okay. Now, plus, munch that. Plus minus, well, the question is there a token plus minus? Does anybody, can you think of anywhere in the language where you use plus minus together? See, I don't think there is. I don't think there is a plus minus token. So that means that would be the maximal token, then minus minus. Now, what does that mean? Post increment X, add it to pre-increment Y. Okay, let's see if Java likes that. See, now it tokenized. Okay, because that broke up the. Okay, now let's see. So you can kind of play games with that. You could also make this work as minus plus plus. Now Java would be able to figure out how to tokenize that. Okay, because there would be maximum munch, subtraction, and then plus plus again. Okay, so this one Java can tokenize, but you put a plus in there, even though, see, that makes sense to Java. This should mean the same thing to Java, but it doesn't. The tokenize, see, this is why you have to understand tokenization. Things that you would think would work, like, okay, if a minus works there, a plus should work there, but it doesn't. And the issue is the tokenization algorithm. The tokenization algorithm now gets messed up. Plus plus, plus plus doesn't work. You can't have two increment operators in a row. You can't have two increment operators in a row. Okay, so now the tokenizer screws up on you. Oh, one thing about this is you shouldn't be writing code like this. Okay, if you write code like that, your boss is going to scream at you. Okay, you don't write code like that. You space things to make things legible. You shouldn't be writing this. You should be either writing something like that, and you should be writing something like that, or you should be writing something like that. You're supposed to space your code readable, but that doesn't mean that first of all, you may be reading code that somebody else wrote and you have to make sense out of it. So you may have been given the code written by an idiot and he wrote that, but you have to make sense of it. So you got to sit there and go, what does that really do? You have to, some idiot wrote that, but you have to know what it means because you have to read their code. So you have to realize it means that, not that. Okay. That's why nobody should write code like this, but that doesn't mean people don't. People will write stupid things like this, and you have to be ready to understand it, and then your job is to fix it. If you ever see code like that, then you should fix it by doing that to it. Okay, but you have to understand. You still have to know what these things mean because you may be faced with them one day. Okay. There's a whole bunch of places like this where the tokenizer does weird little things. There's lots of, like, here's a famous one. Oh, darn it. I didn't mean to close that one. I meant to. Here's one that's this was a problem in C++. In generics, I can say something like list of, okay, that's a list of integers, right? Okay, equals new list. Okay, there's an empty list of integers. Okay, what if I want a list of lists of integers? List of integer. Close one list, close another list, equals new list. Does that look familiar to you?
Is that a bitwise shift?
Yes, that's the bitwise shift operator. The tokenizer needs to be really clever here. The tokenizer is not supposed to say bitwise shift operator. It's really supposed to say what?
close both of those lists?
Well, it's supposed to say, it's supposed to not use maximal munch. This is one place where it's not supposed to use maximal munch. It's supposed to say, this one, it's supposed to say essentially that. This one closes that one, and this one closes that one. So it's not supposed to do. Now, older C++ compilers could not tokenize this. You'd get a compiler error message in C++ when you wrote that. And in older C++ compilers, you were taught you have to tokenize this yourself. You got to put a space there. And for years in the C++ language, you had to tokenize that thing yourself. So people got in the habit of writing it like this: a list of space, list of integer space. And then finally, it was hard for them to write the tokenizer that would break the maximum munch rule here and not use maximal munch in this one special case. The Java compiler doesn't have that trouble. The Java compiler doesn't have that problem, but C++ did for years. For years, people were taught to type that. They had to tokenize themselves. If they relied on the compiler, it would do the wrong tokenization and turn that into the shift operator and then give you a compiler error, a really weird compiler error message. Okay, so there's these weird little corner cases like this where tokenization actually matters, where if here you'd get a weird error message. In the older C++ compilers, you'd get a weird error message because that was tokenized wrong. And over here, you have to realize, well, this thing does have a tokenization, and you have to figure out what it is. You have to know that it's this one, not that one. And then, then you get weird things like, why does that tokenize, but why does that not tokenize when they look symmetric to each other? That one tokenizes and that one doesn't tokenize. Okay, but they, usually when two things are symmetric like that, when you replace a minus with a plus, it's the same thing. This one does minus, this one should do plus, but this one won't tokenize. This one, you shouldn't write it that way. You should tokenize it yourself. And this one, if you want it to make sense, you have to tokenize it yourself. Okay, so tokenizing is taking here's another example of this. From the point of view of the Java language, none of this white space, well, most of this white space doesn't matter. Okay, but that one does. See, now I've got a variable called int x. There is no variable called int x. That white space matters. Okay, but here, that's not a token. That's how many tokens? How many tokens are in there?
That's 3.
3 tokens. How many tokens are in this?
3.
Still 3
That's-
tokens. Yeah, still 3 tokens. How many tokens are in that?
That's still 3.
Probably, because that's going to be lumped as the integer positive 12. Okay, so that should be that's like, if I do this, that should tokenize as negative 12, not as the negation of 12. That would be 4 tokens. See, if I space it this way, that's 4 tokens. If I space it this way, that's 3 tokens. My guess is Java treats that as 3 tokens. x2 equal. Now, what about that?
Don't you get an error?
Yeah, what's the error?
You can't begin a variable name with a number.
Right. So this does not tokenize. See, if it tokenized, it probably tokenized as a 2 followed by an x2. So it probably tokenized as int 2 x2. it probably did not tokenize as a variable name beginning with 2. It probably tokenized as int 2 x2. But what's wrong with that? Int 2. Oops. It probably tokenizes like that. What's wrong? Notice the error message? Not a statement. Pretty open-ended error message. What doesn't it like about that?
Is it because it's expecting a variable name
Yeah.
after the data type?
Yeah. It's expecting the problem is not that the variable is 2x2. The problem is that after an int, there should be a variable, but there's a literal. So you wrote int literal when you should have wrote int variable. See, it's the same error message because this, I'm pretty sure, is tokenized as that. Okay. So it's now you can't begin there is a rule that you can't begin a variable name with a number. If you do put a number now, but you can let's see. There is no place in Java where you can put a number followed by a variable. There has to be an operator between them. So there always has to be an operator between a number and a variable. You know, unlike algebra. Remember, in algebra, you can write things like y equals 2x. You know, algebra allows you to write things like y equals 2x. What does that mean? Is that a variable called 2x? You know, what does this mean in algebra?
2 times x.
2 times x. Does any programming language let you do that?
No.
The answer is yes. There are a small number of programming languages that let you write things like that. There are a small number of programming languages that let you use what we call juxtaposition to mean multiplication. You have the two symbols juxtaposed next to each other. That is implicitly means multiplication in algebra, and there's a small number of programming languages that actually let you do that. It's hard to accomplish that thing in a language, but there are a couple languages. I don't remember which ones do it, but I know that they do exist. Most languages make you put a multiplication operator in there, okay? Because it's just too hard to make sense of that in a programming language. Humans are used to reading it all the time. In algebra classes, you do that all the time. You write things like that all the time, okay? But it's kind of hard to have a programming language do that, okay? Here, I'll show you why. Here's one reason why. That means x2, right? In algebra, that actually means z times 4. It doesn't mean the variable z4, just like 4z means 4 times z, z4 means 4 times z. Okay, yeah, and people usually don't write it that way, but sometimes they do. Sometimes they'll write the number after the, it's still the rule, juxtaposition means multiplication. But for us in a programming language, that's z4. That's the variable z4. Now, in algebra, you don't have multi-symbol variables. In algebra, you tend to only have single letter variables. So this would be the variable z times 4 in most way people read algebra. So programming languages, variable names can be compound like this. So that's the variable x2. So that's tokenized as x2. Okay, so that's tokenized as x2. Okay. So you can go around, you can play around with this kind of stuff, and you have to like understand how things are tokenized. Like if you don't have white space, See, when you eliminate the white space, things become, you're much more at the mercy of the language for the meaning of things. This is one reason why we tell people to put lots of white space in what they type. Because without it, you're at the mercy of the tokenizer. Sometimes what you write tokenizes well, but sometimes what you write, well, like that one may not tokenize the way you meant it to. You know, that tokenizes, but it may not be what you meant it to. If you meant it to tokenize like this, okay? So you're taught to put spaces, essentially, you be the tokenizer. You tokenize things. It makes it easier for people to read. You're less likely to be at the mercy of the tokenizer itself. And, you know, think like this tokenizes, but, you know, if you change that minus to a plus, then it doesn't tokenize. So you're kind of at the mercy of the tokenizer unless you do that. Then you can change that minus to a plus and it's okay. Okay. So you're taught to do the tokenizing, but you should know how the tokenizer works. Okay. So tokenizing is taking a stream of characters and breaking it up into units. Okay, that's how we define tokenizing. You take a stream of characters and you break the characters up into units. Like this is the unit int. I need the space there to break that one up. So I have to put that space token there. Okay, but I don't have to put a space token here because the tokenizer says, well, Z, that's a new token by itself. Then, okay, now, like that, what does that do? What did putting that plus in there do?
Isn't it just a variable name?
Where? Say again?
The whole thing, isn't it just a variable name?
No. Oh, it doesn't like it anymore. Well, what am I doing wrong? Oh, I'm sorry. I got rid of the, see, I changed X to X2. So that mistake was this X, I had changed the name of it. Okay. Now go here, put a plus there. Oh, I'm not allowed to do that on a declaration. So do it here. Yeah, see, okay. I could not put a plus there, but I could put a plus there. Okay, so what was I doing? What did the plus there try to do? And what did it do there? Why was I allowed to put plus?
It adds X to C in the second one, and the first one it was seeing it as the name of the variable.
No, that's not quite what it is. This is okay. I can put a plus there. It's okay, but I need to know what it means. But I can't put a plus there.
Is it because you don't know what Z is yet? So you'd be saying Z is equal to Z plus, and then what's after that?
Well, okay, how did this tokenize? Int, what you said is right. So, but you have to explain it in more steps. What's the, so this tokenizes as int, Z, then what?
Plus equals.
The plus equal operator followed by this stuff here, okay? What's wrong with that? Like he said, you can't add, this means add the right-hand side to the left-hand side, but the left-hand side actually hasn't been declared yet. So there's nothing on in this case, there really isn't a left-hand side because you're in the process of declaring Z. So you can't use the plus equal operator in a declaration. You're not allowed to use the plus equal operator in a declaration because there isn't a left-hand side yet. But what did this thing do? Z plus equal the result of all this. So you're taking that result and adding it on to Z and setting that new value into Z. So this is tokenized as Z plus equal this stuff here. Okay, so they both tokenize the same way. They both tokenize the same way, except that this one is this one's an illegal statement because you can't do an increment operator in the process of a declaration. In the process of a declaration, you can only do an assignment operator. Now, if you do this, does that make sense? There's the assignment operator. Well, that tokenized. Well, does that make any sense? Does it make any sense to write 1 plus after a variable name? Is that a legitimate variable name? You can do Z2, you can do Z0. Can you do Z plus as a variable name?
No.
Yeah, you know, how would you like here's the interesting thing, like what is allowed in a variable name? Is Z exclamation mark allowed?
No.
Is Z square bracket allowed?
No.
Well, kind of, isn't it?
As part of an array.
Yeah, if you finish it. Yeah, if you finish it. If you finish it, then yeah, the square brackets make it part of an array. Is Z underscore allowed?
Yes.
Yes, it is. Where do they set these rules?
You mean like where they actually use that, or where they set the
Where do
rules
they
for?
tell you? Where is the rule book on what you can call a variable?
The documentation.
Which is this grammar. It's the grammar. If you dig through this grammar, you have to find it in here. But if you dig through this grammar, is the grammar for variable names, which spells out the detailed rules for what a variable is. Okay, so it would be in this grammar. Now most of the time you learn it by reading a textbook, but the documentation that says this is this grammar here. The syntax of the language that buried in this thing is somewhere going to be the syntax for variable names. Okay, and it'll tell you that, for example, that a variable name can have underscores in it. For example, variable names cannot begin with an integer, but they can have integers in them, and they can have underscores in them. There's a legitimate variable name. Okay, you can have any number of underscores. You can't put an @ sign in there. That won't work. I think the only special character you can put in a variable name is the underscore. I think that's the only special character that I can remember. Okay. The only special character that I can remember is underscore that you can put in a variable name. You can put letters, numbers, and the special character underscore. Can you put that in a variable name?
No.
Why not? Because what is it really?
Modulus division.
Yeah, now that's saying Z for underscore X divided by, well, but now it's divided by 6_3, which is not a variable. If that happened to be a letter, then that would be one variable divided by another variable. That's one long variable there. Okay, so the underscore is not used as an operator anywhere. See, underscore is not an operator. Most of the other symbols are operators somewhere. Less than, greater than, not exclamation mark. Most of the other special symbols are actually operators. Okay, the @ sign is not an operator, but it's used for annotations. It's used as the symbol to mean the beginning of an annotation. Okay, so the @ sign, it's not an operator, but it's used in the language to represent annotations. Okay, what is pound sign? Does anybody remember? Is I think it means something in Java. You can't have it in a variable name. But I can't remember what
Macros.
No, yeah, that would be C++ and C. Java doesn't have macros. Yeah, C uses the pound sign for macros. I don't remember if Java even does use pound sign for anything. It may just not be used for. I'm not remembering offhand a use of pound sign in Java. In C and C++, it's beginning of a macro. Okay, but I don't remember offhand. I'm not remembering where it's used in Java.
It doesn't show as an operator when you look up Java operators.
Yeah, but like @ sign doesn't either. But @ sign means annotation. So and like pound in Java and C is not an operator, but pound means macro beginning definition. So this guy could be in the language, but not as an operator, as something else. So like annotations or macros. Like Java doesn't have macros, but it does have annotations. So I don't remember a use for pound sign in Java. I don't remember offhand any use for pound sign. Okay. All right. So underscore is reserved as not an operator so that you could use it in variable names. Okay. So the grammar spells these things out. Okay. The tokenizer tokenizes that as one big variable name. Okay. So if you write something like this, the tokenizer has to work pretty hard. Variable name, equal sign, variable, post increment operator plus y. Okay. So the tokenizer had to do a lot of work there. Okay. Oh, what about that? Does anybody remember the rule in Java? Remember, you can't put a number at the beginning of a variable. Can you put an underscore at the beginning of a variable?
Yeah, I see most people do it with private.
Yeah, a lot of people. Yeah. You're allowed to begin a variable name with an underscore. Oh, but see, now I don't have a variable z anymore. Okay, so there now there's my z back again. Oh, then I can't have the plus equal there. But that's a legitimate variable name. See, you're allowed to. See, you're allowed to have a variable with a leading underscore. You're warned it's not a good idea to do it because the compiler tends to use these underscores the compiler tends to create hidden variables with leading underscores. And if you start naming your variables with leading underscores, you can end up with weird errors when you accidentally conflict with something the compiler is doing behind your back. So you get kind of warned not to use variables with leading underscores because you don't want to take a chance that you end up conflicting with something that the compiler is doing behind your back by creating hidden variables. The rule of thumb tends to be that compilers use leading underscores for creating hidden variables. So it's considered not good programming style to have variables with leading underscores. So sometimes people do it, but it's not considered a good idea. Okay. All right. So this is why in a book like this, in a course like this, we talk about this idea of, where is it? Tokenizing. There's a fair amount going on here. And that's the first step of a compiler. The first step of a compiler is to take your program and to chunk it up into these tokens. Okay. Now, most people write their code in a way where the tokens are obvious. Okay. So that's what you should be writing. You know, this one's okay because the tokens are pretty obvious. This one's not okay because the tokens here are not at all obvious and they might even be misunderstood. You know, this one could be misunderstood because remember, it could be that guy or it could be that guy or it could even be that one. But it is that one. But you know, you have to know that it's that one because it could have been any one of these three. Okay. So you should write your code in a nice way. So the rule of thumb is put spaces around your tokens. What you think are the tokens, put spaces around them. Okay. You should tokenize your code and not rely too much on the tokenizer. Okay. And not write run-on lines of code like that, especially like with for loops. You know, it's kind of annoying when people write for int I equal 1, I less than 10, I plus plus. That gets real annoying real fast. Okay, you shouldn't write your, now the tokenizer will tokenize that properly for you, except that I forgot a semicolon. The tokenizer will tokenize that properly for you, but it's not nice to write code like that. Yeah, it's hard to read it. And depending on how complicated your code gets, you may actually not realize that the compiler may stop tokenizing the way you think it's tokenizing it, and it might start tokenizing it its own way. And so you got to be careful. Okay, so you should tokenize it yourself. Okay, you can do that. You can do that. I don't know what I typed it. That's legitimate. That operator still acts on that guy. Though very few people write it that way. Very few people put a space there. But it's same like over here, you can do that. It still means pre-increment y. Though most people, just to make it, you know, they read it like that. They attach that operator to the operand, just to kind of makes it a little bit easier to read. So the tokenizer will tokenize this the same way. That variable followed by that operator. So that operator is still acting on that variable. Just a little bit easier to read if you write it that way. You can also space your semicolons like that. Most people don't. Most people don't, but some people do. Some people take an extreme point of view of spacing everything out. You know, so they even space out their semicolons. Tokenizer doesn't care. You can even write your for loop this way. Almost nobody does it. You know, almost no, you know, the three parts of a for loop. Almost nobody ever does this, but you're allowed to. White space doesn't matter. Okay. Every once in a while, people do write it this way if they're writing really complicated for loops where they do a lot of stuff in this step. You can do multiple things in these steps, like you can declare several variables. You know, you don't have to, you can declare several variables with you use the comma operator. You separate them with the comma operator. So you could do, now here you can only have one Boolean expression. You can't say something like this. That doesn't make sense. That's not a Boolean expression. But you could say and, you know, so you could say I less than 10 and j less than 12. Okay, so that's one Boolean expression. There's no comma operator here, but there is a comma operator in this part. So you can declare multiple variables, and you can use a comma operator in this one too. You can do this. You're allowed to use a comma operator there. See, that compiled. That weirdness compiles. So, you know, you can write, you know, you can you can do weird things in these languages. There's the, and then you could take this and untokenize it, and make it real unreadable. Oops. And it's still the same thing. It's just more unreadable now. The only white space that had to stay there was the one after the int. It's still legitimate Java, okay? But I'm relying on the tokenizer now to figure everything out. And that one does, there's nothing tricky in this one, but notice that that's one continuous, whoops. That's one there's no white space in there. That's just a stream of characters. And it's the job of the tokenizer to break that up. Token, token, token. Pretty much here, it's one letter tokens. Notice that tokenizes real, everything's one letter token, but it doesn't have to be that way. Well, here's a 2-letter token. I'm trying, there's not too much I could do. Like if I put, there's a 2-letter token, 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 okay? Token, token. That's a token by itself. That's a token by itself, okay? All right, so the first step of a compiler is to take your stream of characters and chunk them into a stream of tokens. So the first step of a compiler is something called the tokenizer, and I don't think he drew a picture of it. It's usually thought of as taking in, the tokenizer takes in a stream of characters and gives you out a stream of tokens. Okay, so it takes in, this is just character, 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 character. But what comes out of the tokenizer would be the token public, the token class, and then the white space would disappear. So see, that space doesn't come out of the tokenizer. What comes out of the tokenizer would be the list, public token, class name here token, brace token, public token, static token. There would be no spaces in the tokenizer stream. The tokenizer removes the spaces. The tokenizer also famously removes the comments. The tokenizer would put out an int token, a variable token, an equal token, an X token, a post increment token, an addition token, a Y token, a semicolon token. Skip all this. It's not part of what the tokenizer spits out. Then an int token, a Z token, an equal token, an X token, a plus plus token. So the tokenizer famously removes comment. It keeps the punctuation, but it removes the comments. They're not part of, they're treated like the white space. They're treated like the spaces here. The tokenizer says token, token. What's in between the tokens? Well, the tokenizer produces a list of tokens. So this is the first element of the list. This is the second element of the list. This is the third element of the list. There's nothing between them. They're just, the tokenizer literally produces a list of tokens. It takes in an array of char. That's string. This is essentially one big string. It's an array of char. It's one big string. And it takes the array of char in and produces a list of token out. Okay. All right. So that's kind of interesting. The tokenizing can be actually a tricky thing to do. Writing tokenizers is hard. Writing that program that takes this stuff here as input and produces the list of tokens is actually a fairly difficult thing to do. That's why I told you the story about how C++ couldn't tokenize the list of integers. it was just too hard to write a tokenizer. It took them a long time to figure out a strategy for writing a tokenizer that could tokenize that idea of a list of a list. That one thing was really just kind of hard. Okay. Yeah. So, and maximal munch turns out to be not the rule you use all the time. So maximal munch is a rule that tokenizers only can use most of the time. But when you get to that list of list things, then you have to not use the maximal munch. Oh, that's right here. It is here. This is not maximal munch. This one is token followed by token. So this is this is treated as 2 tokens. But if you do it later on in your code, if you had something like int x equals y shift 2, that's the that's the shift operator. I think this will compile now. What did I do? Oh. Oh. What did I do wrong? Oh. To get this to compile, it's a little bit of work. Okay, see, finally compiled. This is interesting. That tokenized differently than that. There was an example where that one is a shift operator. That is tokenized as close angle bracket, close angle bracket. So maximal munch was not used there. Okay, but what we saw earlier that maximal munch was used here. So writing that kind of writing all those rules is hard. Tokenizers are notoriously difficult things to write. Okay, so and languages like Java and C++ are notoriously hard languages to write tokenizers for because the languages are so complicated. There's so many weird things going on. That being different than that. Okay. Okay. So from a programmer's point of view, you need to know what a tokenizer is, and you need to know why you need to know what a token. You have to know that there's odd things going on. Like luckily in Java, you don't have to worry about that. Like I tell you, older C++ compilers, you had to do that. Otherwise, that thing was tokenized as shift operator, and the compiler complained. Because the compiler sees the output of the tokenizer. So if the tokenizer spits out that as a shift operator, the compiler just says list of integer shift, and the compiler complains. The compiler sees the output from the tokenizer. It doesn't see your original code. So it's the tokenizer that gets the first pass at what your code means. And if the tokenizer gives it the wrong tokenization, the compiler can't do anything about that. Okay, and that's why down here when we had 5 pluses in a row, the compiler, once the tokenizer gives this a bad tokenization of plus, the compiler can't go. The compiler is not allowed to go back and say, but there was a better tokenization of that. Once the tokenizer gives it a bad tokenization, the compiler is stuck with that. the compiler sees what the tokenizer produces. Okay, and the compiler doesn't like that one. The compiler doesn't like what the tokenizer produced from there, but you can tokenize it correctly. Okay, so tokenization is a real interesting topic. If you took a graduate course in compilers, that's one of the things that would be in the course. A graduate course in compilers would start talking about, okay, how do we actually really write a tokenizer? Okay, and it's tough. It's a pretty difficult thing to do. Okay, so then run out of time. Let's see. At the end of chapter 2 in the textbook, there's some nice exercises on constructing simple grammars. And I think what we'll do is we're gonna do some of those exercises in class on Tuesday. We'll finish this chapter by doing a couple of the exercises of constructing a simple grammar, because it's a good practice for understanding grammar. If you can write a real simple grammar, it helps you understand more complicated grammars. So that's at the end of chapter 2. There's some nice examples of write a simple grammar for a simple language. We'll do a few of those on Thursday. So that's how we'll finish this chapter. And then we'll do the hard part, the next chapter, which is where syntax meets semantics in grammars. That's kind of the harder thing. So we'll start that. We'll finish chapter 2 by writing a couple examples of grammars, and then we'll start chapter 3. Okay. So if you have questions about the homework, send me an email or come to office hours. The homework is due next week. So when's that? The homework's due on Tuesday. Okay, so the homework is due on Tuesday. And if you have questions about the homework, send me an email or come to office hours. And like I say, on Tuesday, we'll finish chapter 2 by doing some of those homework problems, and then we'll start chapter 3. Okay? Anybody got any last minute question? Any question at the end? Anything? Okay, so have a nice, okay, I'll stop here. Have a nice weekend and see you again on Tuesday. Bye.